Welcome to the first presentation in Unit 2 entitled Rate of Success. The three lesson cycles that we're going to do in Unit 2 focus on the big ideas in physics, with the first one being the idea of a rate. So we have success as a lousy teacher. It seduces smart people into thinking they can't lose. So the learning objectives are that you be able to identify values as being rate, that you be able to differentiate between average and instantaneous rates, and that you be able to predict the value of a rate at a given time. And that's going to be mostly graphical. So, physics, like all science, is dependent on measurement. It's heavily dependent on measurement. If you can't measure it, it never happened. So, the measurement of a variable can change over time. And that's the key thing that's going to be associated with rate. In fact, time is one of the seven fundamental units of measure that we discussed in Unit 1. So, rates are defined as the measurement of a variable per unit time. So, the key thing for all rates is you have some unit, whatever unit that is, divided by some unit of time. Now, it doesn't matter what that unit of time is. It could be seconds, it could be milliseconds, it could be hours, it could be days, it could be millennia, I guess. It doesn't really matter. As long as you have some unit divided by some value of time, that's going to be a rate. So the greater the rate, the more change there is in a smaller amount of time. So if you were to look right here I'm producing a larger amount in the same amount of time than I am here. So the blue line is much slower and the red line is faster. Now eventually it catches up because the rate slows down, but rates can be determined either using data or graphically. So, big idea number one is that the rate of change for a variable can provide a great deal of information about a system. Okay, a lot of times we're not interested so much in a measurement, but how that measurement changes as a function of time. So, rates in science. So, the rate does not mean the same thing in science as it does in common vernacular. Okay, you have the whole idea of rate by teacher, which is you saying from 1 to 10 whether or not your teacher is a good teacher or a bad teacher. But when we talk about ratings in science, we're talking specifically about measuring a value as its relation to time. So it's a specific ratio involving time. Now remember, a ratio is where you divide two variables together. So you could have something that we've worked with before, like density, which is mass divided by volume. Density is a ratio of mass and volume. However, density is not a rate because this term is not time. If it's not time, it can't be a rate. So there's a lot of overlap between rates and ratios. You can determine the rate from data. So whenever you look at data, you can take a measurement and you can divide it by the change in time. And the key thing here is that determining the rate in this class is actually going to require us to have a minimum of two data points. Okay, so you have to be able to say, here's point 1, here's point 2. I need to be able to subtract those two values to get the change in the measured value. Okay, a lot of times they'll say it's delta x or delta something because delta means change. And then finally you'll have the change in time on the bottom. So this is an example of a rate. Specifically, this is the rate for velocity. You can also determine the rate from a graph, okay, as long as time is the independent variable. Now remember, the independent variable goes on the x-axis. So if you were to find the slope of this, the slope would be equal to distance divided by time. Well, the slope is going to be the same thing as we did here, where you're doing the change in one value over the change in another. So the slope of the graph determines the rate, assuming that that the independent variable is time. Seconds, years, months, seasons, games. Even a game would be considered a unit of time. Okay, rate. The average rate uses the slope between only the first and the last data point that you are interested in. Okay, that you are interested in. So for example, if I want to know what the rate is between 0 and 5 seconds, I use the point at 0, 0 and 525, and those are the only 2 points that I use. If I'm interested in over 10 seconds, I would use this point, and that would allow me to figure out my rate. Okay, so in other words, if you find the slope between the 2 points that you're interested in, that represents the average. Now, if you notice, the average is very different depending on the time frame. The speed or the velocity that I have in this case is going to be much faster here than it is here because these are average values. Okay, so you have to understand that. You have to use the first data point and the last data point that you are interested in. Okay, none of the other data points in between matter. Now, you can find an instantaneous rate. The instantaneous rate is at a given point, what's the rate? It's very, very difficult to do this, and we're going to talk about why in just a second, unless you have a straight line. If I have a straight line, the slope is the same everywhere. Because the slope is the same everywhere, no matter where I go on that line, the slope is going to be, in this case, 5. So if I want to know instantaneously how fast it's going at 3 seconds, it's 5 meters per second because the slope never changes. Okay, so the first data point is 0, 0. The last data point is 1, comma 5. Okay, anywhere along that line, the instantaneous rate is going to be 5 meters per second. That's going to be very different if you have a curve, which is what we're getting into now. In reality, the instantaneous rate is much more complicated. Okay, so for example, when you have a curved line like you have here, okay, the slope is continually changing. So if I were to try and draw, the slope here at this point, that's the slope, that's the slope, that's the slope, that's the slope. So the slope is continuously changing. So now how do I define instantaneous? Do I say from 0.25 to zero point 0.2? That's instantaneous. Or do I say 0.25 to 0.249? Or do I say 0.25 to 0.249999999? So instantaneous rate is actually a really complicated issue if you do not have a constant slope. Okay, constant slope makes it much, much, much easier, but if you don't have a constant slope, it becomes very complicated. In fact, it's so complicated that Newton, who is the primary person who we're studying in this class, invented a whole new branch of mathematics called calculus to answer these types of questions about, well, how fast is it going instantaneously at this point? So calculus uses 0 as the change in time. But if we were to use just our normal math and say delta x over delta t, and we were to plug in 0 here, you'd get a value of infinity. So at this point, Newton had to invent this branch of calculus, and Leibniz is also commonly credited for doing it at the same time, to develop these sort of mathematical functions. Now, we are not going to get into this. Calculus is well beyond the scope of this class, but that's where this comes from. The idea that you wanted to figure out how fast it's going right now is why they invented this calculus branch. All right, so what is the average rate based on the graph? So if you were to look at this, based on the assumption, it means I look at all the data points. If it doesn't give me a specific data point, I know I have to use all the data points. So I start at 0, 10, and I end at, we're going to call it 11, and we're going to call it 14. 11, 14. If you have 0, 10 and 11, 14, you can calculate what the rate is between those 2 points. You take your y's. It's just like you would find the slope of the line between those 2 points. It's really hard to draw a straight line because it's such a small amount. So you see that slope is not very much, and so you should get a small value. So in order to find the slope, remember you do the change in y over the change in x, change in y over the change in x, and you would say 14 minus 10 divided by 11 minus 0. And you'd say 1.4 divided by 11, and you're going to get an answer somewhere around, we'll just call it 1.3. So the slope of this line is going to be 1.3, which is a relatively small value. At no point is this object necessarily going 1.3. That's the average over the whole trip. Now it says, what is the rate between A and B? Okay, so we're going to go ahead and erase this so we can see between A and B. And if you use just points A and B, you have the point 0, 10. I'm going to change colors just so it's easier for us to. 0, 10, and you have the point 2, 10. Well, when you do your change in y, 10 minus 10 is 0. And it really doesn't matter what the bottom term is at this point. In this case, it's 2 minus 0. 0 divided by any number is still going to be 0. So it really does matter what time frame you're looking at. You're saying, okay, well, how fast is it going here? Or what's the rate here versus what's the rate here? In fact, you can look at all these points and see where the rate changes. Here, the rate is something, and then all of a sudden, the rate changes. And then all of a sudden, the rate changes. And then all of a sudden, the rate changes. And so you can see these clear, distinct points where the rate changes. Next, it says, which of the following will have the rate of temperature increase for the overhead measurement. So the first thing you want to do is you want to eliminate all the extra information. I don't need to know about reboiler temperatures or pressure or reflux ratios. All I'm interested in is time and overhead. So you have to be real careful because you look at this data and you go, oh, look, they're all about 5 minutes apart, but they're not. A lot of the readings are 10 minutes apart, and some of them are even 45 minutes apart. So it becomes really important that you look at the data as a whole and say, okay, which one is going to be the smallest time ratio? Or the smallest time value, because the smaller the time value, generally the bigger the ratio is going to be, because the smaller number you divide by, the bigger the whole number ends up being at the end. Once you identify these smaller values, you also need to look at the idea of where is the greatest change in temperature between these data points. And so it may take you a while to kind of scan through these. You may try doing a couple of the bigger ones out just to see what they're going to be. But when it comes down to it, if you were to look between 1925, let me go ahead and highlight this for you, between 1925 and 1930, you have a pretty big temperature change there. You actually have a temperature change of about 15.8 degrees. Okay, if you have a temperature change of about 15.8 degrees, that's a pretty big temperature change. And it all happens in 5 minutes. So that's going to be the greatest change in temperature per minute that you've got, which is the rate, which ends up being about 3.16 degrees Celsius per minute, which is about 5 degrees Fahrenheit in 1 minute. So if you can imagine being in a room, where it suddenly changes from 75 degrees to 80 degrees in a minute, that's a pretty drastic change there. So in this one it says the rate of position versus time is given a specific term, velocity. So what would a graph of velocity versus time look like? So in order to do this, we're saying that the slope, okay, here's the slope, is given a term v. And you have the slope here, which is given a term v. And the slope here, which is given a term v. And the slope here, which is given a term v. The slope here, which is v. And the slope here, which is v. So you can see that if you were to look at all these points right here, you have some pretty drastic changes in velocity. The velocity actually is a negative number. The reason why it's a negative number is because the slope is negative. It's actually going down. So if you were to do the rise is actually negative because it's moving down as it proceeds through the run. So because of that, we would say this thing has a negative value to begin with. Now, if you were to look, it starts out as a pretty small negative number. I mean, this is pretty close to horizontal. So what I'm going to do is I'm going to start it at 0 and say that it's, pretty close to horizontal. But as time proceeds, the slope gets more negative and more negative and more negative and more negative. So you get something that looks like this. Now this is a pretty tough thing to go back and forth between these graphs, and you're going to spend a lot of time with it when you talk about Unit 2 motion. There's going to be some specific activities that you do to see if you can go back and forth between these graphs. So you can use rates to predict just like other variables. The rates can predict values that you don't want to specifically measure. And you see an example here. This is a month by month. So you see this trend that you see in reported cases of the Zika virus and then the CDC prediction. Okay, and then here's interpolation, like we talked about before. And interpolation is an estimate of values between. It is generally more accurate than extrapolation, but at the same time, it's a reasonable estimate, but it's still not as good as an equation. Okay, next you have extrapolation, which is an estimate or prediction of something that is beyond what you experimentally tested. It's generally a little bit less accurate because you tend to see things that curve off or they don't follow the trend further on. So because of that, they're not nearly as accurate as interpolation, and they do represent an estimate for the value that you would get if tested. But once again, it's not anything. It's not necessarily reasonable. So it says, what would you predict the global average temperature to be if the jobs program increases the number of pirates to 7,500? So this is an example of something that's utterly and completely ridiculous. If you were to graph the number of pirates versus the global temperature, you'd notice that as we get less pirates, the global temperature goes up. So if you look at this data, you say, oh, well, we'll just have more people become pirates and then, global warming won't be an issue. Well, the problem with that is this is a fallacy. This is if you look for relationships between data that aren't experimentally tested, you can find patterns wherever you look for them, but those patterns don't necessarily mean anything. But if we go with this based on the data, this right here is our 7,500 number. Okay, if we were to go up to 7,500, you should realize that we are doing interpolation. If we're doing interpolation, we're looking at a global temperature around 15.1 degrees, maybe 15 degrees, depending on how straight you are with your line there. Next, it says, what would be the danger in extrapolating based on 1964 to 1967? If you were to look at the 1964 to 1967 data right here, and you were to just continue that trend, here's what the extrapolation would look like based on that trend. So you look like it and you say, wow, in 2009, gas prices are going to be expensive. It's going to be 50 cents a gallon. Okay, so it'd be very, very wrong to extrapolate based solely on those 3 years worth of data. Now, if you were to look between 1979 and 1982, okay, that's this trend right here. If you were to continue that trend up, you're looking at something that's going to be approximately, $7 a gallon for gas in 2009, which is again completely ridiculous. So whenever you're working with data, be very, very careful when you decide to extrapolate. Now, what are the limitations that you should use when extrapolating this graph? Now, if you look, this is actually a pretty interesting graph because it's the cost per hard drive per gigabyte per year. So if you were to look in 1995, for you to have a gigabyte, it cost you almost $1,000. Now, this is a logarithmic scale, right? Because it's a logarithmic scale, each line represents a change of a factor of 10. So it's going 1 to 10 to 100 and so on and so on and so on. And that's so we can get this data on the graph. Now, if you were to look at this thing, you'd say, wow, almost $1,000 for a gigabyte. Now you carry around a flash drive in your pocket that's 10 gigabytes or 16 gigabytes or 32 gigabytes, and it costs like $10. Okay, so you see this pattern downwards. Now, what is the danger or the limitations in extrapolating? Well, extrapolating is going beyond the tested data. If you were to continue this trend downward, you'd eventually get to the point where it's less than 1 cent. Are they ever going to give hard drives away for free, or are they ever going to, go negative and actually pay you to take a hard drive? And that doesn't make any sense. Now, if you were to go the opposite direction and you were to try and extrapolate before 1980, you'd say, wow, somebody could have bought a hard drive for, $10 million, when in actuality they didn't exist at that point. So you do have to be very careful when you decide to extrapolate.